All right, so we'll get started. Again, this is a final reminder for homework number 10. That's due tomorrow. Okay, so make sure if you haven't finished the problems, make sure you finish them by tomorrow midnight. And number 11 will be due next Monday. Okay, so it'll be due on a Monday instead of Tuesday. Um, Final exam is scheduled on Wednesday, the 21st. That's at 7:50 a.m. Through 9:40 a.m. Okay, and we'll meet in faculty 108. Okay, so that's the reminder items. So let's take a look what we learned last time. So last time we talked about the ray aspect of light. So basically, the light travel in the same media in a straight line. It changes direction when it interact with material. For example, it hits a surface or get enter refracted into the material. Then the direction will change. Okay. Um, so first, if light is interacting with the surface, then it will get reflected. The incidence angle is equal to reflected angle in this case. This is called law of reflection. So theta I is the angle the incident ray makes with the normal direction of the surface at that point. And then theta I is the reflected angle the reflected ray makes with the normal surface at that point. Okay, so theta I equal to theta I. Then we talk about the law of refraction. Before that, we took a look at how speed of light can be measured. So you can have rotating mirror here. You have light source. You know the distance that light travel. You know the distance from this fixed mirror to this rotating mirror, and then from the light source to rotating mirror to the rotating mirror to your detector, the viewing telescope. You can calculate how much time it takes for the light to travel such distance and then divide by the time. The distance divided by the time it takes will give you the speed of light. In theory, speed of light is almost 3 times 10 to the 8 meters per second. Okay. When the light enters a medium, then the speed of it will be reduced by a factor called index of refraction, m, small n here, that equals to the speed of light in vacuum divided by speed of light in the medium. Okay, so c is the speed of light in vacuum, and v the speed of light in the medium. So in that case, then the light will hit the surface, part of it will be reflected. That's governed by law of reflection. So reflect angle equal to incidence angle. And then part of it will be refracted, enters the median. So theta 1 is the incidence angle, theta 2 is the refracted angle in the median. Then this will satisfy Snell's law of refraction. So N1 is index of refraction in median 1. Sine of theta 1 is the incident angle equal to N2 index of refraction in the second median times sine of theta 2, get the refracted angle in the median. And in the case if you have light enter from a index of refraction that is greater to a smaller index of refraction median, so then theta I would be smaller than theta 2 according to Snell's law, because N1 is greater than N2, so then theta 1 will be smaller than theta 2 in that case. So as you increase theta 1, then theta 2 will reach 90 degrees first. When that happens, after you further increase angle, the incident angle theta 1, the total internal refraction will happen. Now, no part of light will enter the second medium. Okay, when that happens, we call this total internal reflection. We also took a look on dispersion, which means if you have light hit or white light hit the prism, so sunlight is a white light hit the prism, so then different colors in sunlight in the white light will be separated out. So that's called dispersion. All right. Now, today we'll be moving on in this chapter. We'll take a look on image formed by mirrors. And the focus will be on spherical mirrors. But first, let's take a look on plane mirrors, okay? So to visualize the image formed by a plane mirror, we can use the ray diagram. So basically, you take 2 points from the object, and then you draw 2 rays out of that object, hit the mirror here, and then applying law of reflection, you'll see where the image of the object is. Okay, so for example, the base of the vase here, you can draw 2 lines over here. They will get reflected into your eye. Then these 2 rays, they hit in your eye, but they do not meet, right? But you can back extend them. So then it looks like they are coming from a point behind the mirror here to your eye, both of them. Similarly, for the top of this flower over here, you can draw 2 rays, hit the mirror, and then get reflected into your eye. Then you can back extend those 2 rays, enter your eye. They appear to be coming out from a point that behind the mirror. Okay, so that's the top of the image for the top of the flower here in the mirror. So this process called the ray diagram. From geometry, you can verify that DO, which is the distance of object to the mirror, is equal to DI, which is the distance of image to the mirror. Okay, and so this is the geometry here. You can see that. So this theta, the 2 are equal to each other. Instance angle equal to reflected angle. And then this angle should be the same as the theta. Okay, so this 2 will be the same. Then this phi and this phi will be the same. Okay, then these 2 angles are the same triangles, or these 2 triangles are the same triangles here. So then DI will be equal to DO. Okay, in that case, you can also see the size of it will be the same. Okay. All right. Now let's then take a look on a spherical mirror, which means the mirror is curved. Okay, you can make a spherical mirror by cut a piece of a sphere out. Then you can mirror one side of it. So you cut one piece from sphere and then mirror one side of it. So if the outside is mirror, we call this as convex mirror, because then mirror is convex. Okay, if the inside, the other side is mirror, then this is called a concave mirror. Okay, because then the mirror is concave. All right. For spherical mirrors, there's a central axis. Okay, so that's connecting the center of curvature to the center of the mirror. And there's a center of curvature. So because this is curved mirror, so this is center of curvature. Okay, this central axis is also called principal axis of the mirror. Right. So in the figure here, left hand side, this is a concave mirror. On the right hand side, this is a convex mirror. So the inner side is the reflecting surface. And then on the right here, you have the outer side to be the reflecting surface. Okay. All right. So if you have parallel rays hit the spherical mirror, in the case of a convex mirror, so then you have then the parallel rays hit the mirror, they will be reflected according to law of the reflection. You'll see theta equal to theta. Okay, so then it will appear that these reflected rays will meet at the focal point behind the mirror over here. So they do not physically meet, but if you back extend them behind the mirror, then you'll see they will come at the same point F. This is called the focal point. Okay, and then this from the focal point to the mirror, this is called the focal length. Okay. And for a concave mirror, you will have the parallel ray comes in, then they will get reflected, and then they do meet physically at the focal point here, in this case, concave mirror. Okay. Now, typically, you cut a small piece from the sphere. So then let me just back off one slide here. Then the curvature here is very small. So this is small piece. So the angle here will be very small. Okay. So if you can approximate angle close to 0, you can imagine this is smaller and smaller. So you can see then this is from here to here, C from point C to F, and then from F to this guy, the surface over here. So you can see this angle is the same as this angle, and then this is parallel to this axis. So this should be also theta angle. So this is the focal length should be equal to this guy, right? and then this is also the focal length. So the twice of the focal length is equal to the radius here when the angle is small. Okay. So in that case, then for a convex mirror, the focal length would be equal to half of the radius with a negative sign because the reflected rays from a convex mirror, they do not actually physically meet at the focal point, but they appear to be coming from the focal point. So that's why we put a negative sign there for that purpose. For a concave mirror, actually the reflected ray, if they are parallel to incidence rays are parallel to the center exit, then they do meet at the focal point. So then the focal length is positive of 1/2 times r. Okay. All right. So now let's take a look on the image of the object in the spherical mirror. So we can use three principal rays to find the image produced by either a concave mirror or convex mirror. But let's take a look on the concave mirror case. Okay, you can use a parallel ray, which is the ray parallel to the instance, parallel to the center axis, the principal axis. That ray will reflect through the focal point. Okay, and then you can pick a second one, which is called focal ray, which is the ray goes through the focal point and then hits the mirror. This ray will reflect parallel to the um, center axis. Okay. Finally, you can pick a center of curvature ray, we call it C ray. That ray goes through the center of curvature and hits the mirror. That will reflect back along its incoming path. Okay. So let's take a look on what these sentences means. Okay, so if you have a P ray, the parallel to the center exit will hit the mirror and then get reflected through the focal length. The F ray goes to the focal point, hits this mirror, will get reflected parallel to the center axis. Okay, and then the center of curvature ray, C ray, will hit the mirror and get reflected right back. Okay, so all these three rays behavior, they are governed by Snell's law or the law of reflection. So you can see if this is the center of curvature, if you draw a line connecting to the point where the P ray hits, okay, so then this angle theta will be equal to this angle theta. Now just imagine a dashed line going there, and then this will be equal to that. So then this angle is equal to that. So this is parallel to that. Okay. Center of curvature ray hits the curvature over here. That's the normal direction. Will get reflected right back. Okay. And then similar over here, this is similar to the P ray. Okay. So you can have those three rays, P rays, F rays, and C rays to determine what's the image formed by a concave mirror. You can actually just pick any two of the three, then you will be able to find your image. Okay. So for example, if you have an object here, for the arrow here, you can pick a P ray and an F ray. So P ray will hit this and then reflect back through the focal point. So then you have one here. F ray will hit this and then get reflect parallel to the exit. So then you can see these two rays will intercept at this. That's the image position of the image. So the image is in this case. Okay. When you have your objects beyond the center of curvature, okay, so that means on this side, then your image, you can see this one is the shrinked image, okay, and then it's actually upside down, all right, and then the two reflected rays, they do meet physically at this point, so that indicate this is a real image. You can actually have a viewing screen placed over here. You'll see the image of this arrow over here, okay. So this is the case when the object is beyond the center of curvature. When the object is in between the center of curvature and the focal point, then you can use again two rays, P ray and F ray. You can draw the ray diagram. P ray hits the mirror, get reflected through the focal point, and then the F ray, the green ray here, hits the mirror, get reflected parallel back to the center of it. So then you can see the two rays, reflected rays will meet physically at this point. So then this is also a real image, okay? But this case is an enlarged image, okay? If you have an object that is within the focal length to the mirror, so somewhere here you can see, then you can pick the top of the object here. You can draw two rays again. Just pick two rays. So this is a focal ray. Okay, so the focal ray appears to be coming out of the focal length, hit this one, and then it will get reflect back parallel to the exit, the center exit. Now you can pick a center of curvature ray. It hits the mirror here, get reflected right back. Okay, so you can see the two reflected rays, they will not meet physically because they are diverged. Okay, but if you back extend them, then they will appear to be intercept behind the mirror. Okay, so that means this image, then it's a virtual image. If you look from here, this is a virtual image. It's upside, it's actually upright compared to the object. So then this is a virtual image upright. Okay, so at this point you can see if you have virtual image is upright. So this is the same for the prime mirror as the virtual image as is upright, right? But you will have a real image when the image is upside down. Okay, so in that case. All right, so this is for concave mirror. So depending on where the position of the object is, you can actually have virtual image. You can also have real image, okay, depending on where your image is. And then you can have enlarged image, you can have shrink the image, okay? Also depends on the location of your object. Let me see. I think I want to talk about the image formed by a convex mirror first before we actually derive the mirror equation. So, so for a convex mirror, if you have a object over here, you can draw three rays or two, maybe even two. So again, the three principal rays will work here. But in this case, when you have a P ray that hits the mirror, will get reflected back as if it's coming from the focal point behind the mirror. So in that direction, okay. For a center curvature ray, it will appear to be point hitting the center of curvature, but will get reflected right back. Okay. Focal ray appears to go through the focal point behind the mirror. When it hits the mirror, it will get reflected parallel to the center of exit. Okay. And in this case, because this is a convex mirror, so the rays hits the mirror will be actually further diverged. So in that case, you always will get a virtual image. Okay. So that's for a convex mirror. You always get a virtual image, and you'll get a shrinked image. Okay, so smaller image. Now that's the image formed by a convex mirror. So let's go back here on the derivation for the mirror equation, which actually relate the distance of the object to a mirror and the distance of image to a mirror with respect to the focal length. Okay. So let's take a look here. So let's say if you have an image object here, original height, object height HO, and then you have its image over here. Now you are outside the center of curvature. Okay, this is for the case of when the object is outside curvature, but it will actually apply to all cases if the object is within the center of curvature and in between center of curvature and focal point, or within the focal point. Okay, so the equation itself apply to all three scenarios. Let's take a look on this guy here. So let's draw a ray comes off this guy and then hits the center of the mirror, and then it will get reflected back, right? Because then this angle, these two angles should be equal to each other because according to law of reflection. All right, so then this shaded triangle and then this one, small and triangle here, they are similar triangles because they share a similar angle here, and then they are both right angle triangles, okay? Also, if you draw a ray that is coming through the center of curvature, it will get reflected right back, okay? So then for this shaded right angle triangle and then this small right angle triangle, they are similar triangles, okay? Because this phi and this phi will be the same, okay? Now let's take a look how can we actually relate DO and DI with the focal length F? Okay, so for convex, I'm gonna do stop sharing right now, but also switch my camera here. So you can write out for the first pair of right angle triangle, you can write actually HI over DI, okay, and it's equal to, so in the first pair of triangle, you can see if you do HI divided by DI, then that should be equal to HO over DO, okay. So from the first pair of the um, similar triangles, and then on the second pair of similar triangles on the right, you can write similar equation here. If you do say HI over one side of it, which in this case from the geometry it indicated is R minus DI, then that should be equal to HO divided by, again in the geometry it says DO minus R on the other side. Okay, so you can write those two equations. For this equation, you can rewrite it. If you do HO over HI over HO, then that's equal to DI over DO. So let's rewrite it. HO over HI over HO equal to DI over DO. And then let's rewrite this guy as well. So HI over HO again, this should be equal to R minus DI over DO minus R. Okay. So then you can compare these two equations, you'll come to the conclusion that because the left-hand side, they are the same, so then right-hand side should be also the same. Okay, so should equal to each other. So you can write that DI over DO then should be equal to R minus DI over DO minus R. Okay, now this is a concave mirror. We know that F is equal to 1/2 of R. So that means R is equal to 2 times F. Okay. So we will then replace R with 2F. So then this now becomes DI over DO equals to 2F minus DI over DO minus 2F. Okay, from there. And then this is replacing of the R equal to 2F. At this point, you can do cross multiplication so that DI times DO minus 2F is equal to DO times 2F minus DI. Okay. Now you can distribute DI into the parentheses and then also DO into the parentheses. Okay, so then DI DO minus 2F DI equals to 2F DO minus DO DI. Okay, you're going to move this guy to the left and then this guy to the right. So then you have 2 times DI over DO because this DI DO, this is minus DI DO, so it becomes positive 2 times. And equals to 2F, okay, DO plus 2F DI. Now you can do 2F DO plus DI, right? And then this is 2 DI DO still there. You'll see that this and this will cancel out. 2 and 2 will cancel out. And you can divide both sides by F. Also divide by DI DO. DI DO, both sides by that. After that, you can see on the left-hand side, you'll have 1 over F, right? On the left-hand side, you'll have, so FF cancel out, you'll have DO over DI DO plus DI over DI DO, right? So then this is DO DO cancel out, DI DI cancel out. So then this will give you 1 over F equal to 1 over DI plus 1 over DO, right? So this is the mirror equation, okay? Di is the distance from the image to the mirror. Do is the distance from the object to the mirror. Okay, and then f is the focal length. All right. All right, so then we arrive at this equation over here. All right, with DO being the distance from mirror to the object, DI and the distance from the mirror to the image. F is the focal length. This also applies to convex mirror. Okay. Any questions you guys might have on the derivation here before we move on? Okay, so if you guys are clear, we'll go to the summarize of the image formed by the spherical mirrors. Okay, so first for convex mirror, it doesn't matter where your object is. You're always going to get the upright reduced size image, and that's a virtual image. Okay, so upright is a virtual image. For concave mirror, depends on the location of your object. If you are beyond the center of curvature, you get inverted, reduced size real image. If you are between the focal point and center of curvature, you get inverted but enlarged real image. Okay, if you are inside or the focal point or between mirror and focal point, you get upright enlarged virtual image. Okay, so for concave mirror, you can get virtual image as well, but again, if it's a virtual image, it's going to be upright. Okay, and this in this case, you will get enlarged image for a concave mirror, right? Next, let's take a look on the magnification. So the magnification is defined as the size of the image HI divided by the size of the object HO. Okay, and then this is also related to the distance of the image and distance of object, but equal to minus of di over do. Okay, so you can see this from the derivation here. So if you do hi over ho, then it's going to be, or in this case, I think the first figure here, that's easier to see. So if you do ho over hi, then it's going to be equal to di over do. Okay, so that's from there you can see it clearly. All right, and then in this case, your hi will be negative, so then that's why you get a negative sign for the minus di over do. Okay, for the magnification equation here. All right. So some sign conventions here. For focal length, f is positive for concave mirror, it's negative for convex mirror. Magnification is positive for upright image, and it's negative for inverted image. Okay, so if you have a real image, magnification is negative. Image distance is positive for images in front of mirror, and refers to real image, and negative for image behind the mirror, virtual image. Okay. Object distance is positive for object in front of mirror, and then it's negative for object behind the mirror. So this refers to if you have more than one mirror, then sometimes the image in a mirror is served as the object for the second mirror. Then that image will also get an image in the second mirror. Okay. Let's take a look on one example here. This one says a concave mirror produces a virtual image that is 3 times as tall as the object. If the object is 16 centimeters in front of the mirror, what's the image distance? And what's the focal length of this mirror? All right, so for this one, so you are going to consider mirror equation, and you are going also to consider the magnification equation here. Okay, so this those two equations. You guys can give it a try. I'll let you guys have a try, and then we can take a look on the solution together in a couple of minutes here. All right, so let's take a look on this one here. So it tells us that the object is 16 centimeters in front of the mirror. So that means DO is 16 centimeter. It also tells us that it produces a virtual image that is 3 times as tall as the object. So that will tell you HI over HO is equal to 3. Okay. So in that case, this is the magnification M is equal to that. So you can calculate what's the DI starting from here, right? So 3 equals to minus DI over 16 centimeters. So that tells you your DI is equal to minus 48 centimeter, okay? So the factor is negative because it's a virtual image. The image is behind the mirror. Hobby is asking you what's the focal length of the mirror. Now you have DO, you have DI. You can use this mirror equation to solve for your focal length. So 1 over F equals to 1 over minus 48 plus 1 over 16. Okay. Then to solve for F, you do inverse of it. And then inverse of that. Okay. Inverse of both sides. That will give you F to be equal to it's going to be 24 centimeter on this. Okay. Any questions you guys might have? So if not, let's move on then. Next, we'll be looking at the image formed by lenses. Okay, so so this happens when you have rays hit a surface of a material, and that material is transparent. Okay, so for example, if you have image in front of transparent material, this could be a glass or some like rubber material. Then in that case, the rays will enter the material over here. So let's take a look here. If you in zooming here, assuming this is a curvature, okay, that has a center of curvature somewhere there. And according to Snell's law, you can apply Snell's law to one of the ray here, and then apply Snell's law to the second ray over here. Now this one hits the surface and goes through the center of curvature. So that means this is in the normal direction. Okay, so instance angle is equal to 0, reflect angle is equal to 0. So it just go right through. On this case here, this is the instance angle theta1, this is theta2. Okay, so you can apply Snell's law there, and then you can figure this is going to be deflected into here in this case, and then these two rays will actually physically meet inside the median at some point there. So this is then where the image will be formed. Okay, so you can see in this case, you'll get a real image inside the median here. All right, so for the image formed by Snell's law, according to Snell's law, or like when the light hits a second material. Okay, so usually for the daily applications, we will have lenses. So you have lenses made of rubber or the plastic or glasses. So in this case, you can have two types of lenses. One is called the convex lenses. So then for those lenses, they will converge the instance ray. The other one, the other type is called the concave lenses. So those types of lenses will diverge the instant rays. Okay, so you can have concave meniscus lens or planar convex lenses, which means one side is flat and the other side is curved. In this case, the two sides are curved into one direction, and then you can also have double convex lenses, which means you have this both curved outside. Okay. In this textbook, we will be focusing on the double convex lens and then double concave lens. Okay. On the other hand here. So let's take a look on this here. So if you have a convex lens, so they curve outside, outward, the lens will converge rays hitting to the lens. Okay, so in that case, the parallel ray hits here will converge at the focal point. So this is similar if you have prism that will be able to converge rays on the other side. Okay, so similar to that. But for convex lenses, they convert parallel rays to a focal point. And then for concave lenses, they actually diverge rays, parallel rays to the center axis. And then those diverged rays appear to be coming out of the focal point there. Okay, and this is the similar effect if you have lenses upside down. In this case, for the top piece, and also for a second bottom piece in that configuration. Okay. So for images formed by lenses, again, we can do similar to what we did for the mirror, spherical mirror. So we can use three principal rays, slightly different here. So in this case, P row again refers to the parallel rays to the axis. And F rays is the ray that appears to go through or coming from the focal point of the lenses. Okay, and then middle, we are not using a center ray, center curvature ray. We are using a midpoint ray in this case. But similarly to the center curvature ray, it will go through the middle of lens. Okay, and then will not be deflected. Okay. in that case, the center of curvature ray will hit the mirror and then reflect right back. Okay, in this case, you'll go right through. So this is a little bit different here. All right, let's take a look on the ray diagrams for the three principal rays here. In this case, if you have P rays, parallel rays will hit the lens and then enter the other side of the lens as going through the focal point. And for the middle point ray will go right through. For the focal ray, it will hit the lens and then refract it, in this case, parallel to the center of exit, okay? And then for concave lenses, you will have parallel rays hit this and then reflect it as if it's coming from the focal point. Focal ray will hit the lens and then refract it parallel to the axis, center axis. Midpoint ray will go right through. Okay, so in this case, you can see for convex lenses, they converge rays. For concave lens, it actually will diverge rays. Okay. For the image formed by a concave lens. So then because the fact that the rays are diverged after hitting the concave lens, then it will form only virtual image. Okay. For the convex lens, this is similar to concave mirror. So it depends on where where your object is. Okay, you can form either a real image or a virtual image. If you are beyond the focal point, you'll get a real image. If you are inside the focal point, you'll get a virtual image. Okay. So for image formed by lenses, if focal length is positive, that refers to convex lens, then image could be real. The distance of image will be positive because it's a real image, and then magnification will be negative. Okay. For case 2, if this is a convex lens, again, f is positive, but if you are within the focal point, then you'll get virtual image. Di will be negative because it's a virtual image. Then the magnification will be greater than 1. For convex lenses, focal length is negative. The image you get will be virtual, and Di will be virtual. But magnification will be less than 1. Okay. That means you get reduced image. You can divide the lens, same lens equation, similar as we did for mirror equations, and it turns out to be the same equation here. So you are using two pairs of the similar triangles again here. You can follow the derivation as we did earlier and then arrive at the same conclusion. I'm not going to do that here, but basically you'll get the same equation. This is called lens equation, but it's the same as the mirror equation. So 1 over DO plus 1 over DI equal to 1 over F. And then magnification is the same as equal to the height of image divided by the height of object and equals to minus DI over DO. Okay. For sign conventions here, so focal length is positive for converging lenses, that refers to convex lens. And on the mirror case is the concave lens, concave mirror. Okay, so these two are for the name of them are in the object. Okay, so F is positive for convex lens, F is positive for concave mirror actually. Okay, and then on the other hand, F is negative for concave lens, but F is negative for convex mirror. All right. Magnification is positive for upright image. Magnification is negative for inverted image. Image distance is positive for real image and negative for virtual images. Object distance is positive for real object. So that refers to actually if you have multiple lenses. In the case, if you have multiple lenses, the real image can serve as the object as well, real object as well. Okay, and then DO is negative for virtual object. Okay, so that refers to virtual image being served as the object. All right. Let's take a look on one example here. So this one says an object with a height of 2.54 centimeter is placed 36.3 millimeter to the left of lens with a focal length of 35. Where's the image located? And then what's the height of the image? So you're looking for DI and HI. Okay, so let's take a look on this one here. So it tells you the focal length as a positive number. This means this is a convex length. Okay, so f equal to 35.0 millimeter. So that means convex length or converging length. It tells us that the HO is 2.54 centimeter. And then it tells us the DO is 36.3 millimeter. Okay, so you're looking for DI, you can use the length equation DO 1 over DO plus 1 over DI equal to 1 over F. Looking for DI, so 1 over DI equals to 1 over F minus 1 over DO. Then DI is equal to, you do inverse of the left hand side to get DI, and then inverse of right hand side as well. So that will be 1 over F minus 1 over O, 1 over DO, inverse. Okay, so this is 1 over 35 minus 1 over 36.3 millimeter. Okay, it tells you this is going to be equal to 977 millimeter for your DI. Okay, and then second one is asking you what's the height of the image. So you're looking for HI. You can use the magnification equation HI equal to, or M equal to HI over HO equals to minus DI over DO. Okay, because you can calculate M by using DI and DO, they are given, and then HO is also given, so you can figure out your HI. So from here, you can see your HI is equal to, you multiply both sides by HO, right? So minus DI over DO times HO. So then minus of DI is 977 divided by DO, 36.3, and then times the HO, 2.54 centimeter. Okay, millimeter and millimeter will cancel out. Then you can have your result as in centimeter. So HI is equal to negative of 68.4 centimeter. Okay, that's the height of your image. It's actually a very large image. Any questions you guys might have? You can unmute yourself and then let me know, okay? All right, so if you are clear, we'll then take a quick look on chapter 26, vision and optical instruments, okay? So the fact that we can see things is our eye here, the this is like a piece of the lens over here. So when we see an object over here, actually it's get the rays from that object is get converged, okay, by our retina here, and then we'll form an image at the back of the eyeball here behind the retina. So in the case that if we have some say the four-side eyes, if our eyes are four-sided, then it will not converge the rays to be right on the retina over here. So then we need a correct lens here to be placed in front of the eyeball over here. So then the rays will hit the lens and then be converged before hit the eyeball over here, and then get the right position for the image to be on the retina here. Okay. And on the other hand, if we have nearsighted eyes, then the focus rate will be before the retina over here. So the image will be somewhere here. So in that case, then we need a concave lens to correct the image to be formed onto the retina here, the back of retina over here. Okay. So that's what the lens is doing here. It's a divergent lens. So because it's a divergent lens, then you can see the fact that the image is always smaller. So we actually, if you are wearing divergent lenses, the object you see should be should appear like smaller than it actually is. Okay. All right. So also that for the object, if it's further away, although it's the same distance, so in this case, in part A, in figure A, if the object is further away from your eye, and then in part B, if you are getting closer to the object, so you'll see that the image formed by here and on the retina here. So if the object is further away, then image is smaller compared to if you are closer to the object. Okay, so in that case. So that's why object further away looks smaller than they should be. Okay. Now, if you guys use microscope a lot, so this is what happens when you have microscope. There's a eyepiece here right before your eye, and then there's an object piece over there. Okay, so then for small piece of object to be in front of objective lens, okay, you will form an image. It's just going to be a real image somewhere here, and then through the second eyepiece, it will be enlarged further. Okay, so that's the a simple drawing of a compound microscope. Okay, I think that's how much I would like to mention about this chapter, and then on Wednesday we will take a look on the wave aspect of the optics. Okay, of optics. So this week is the makeup week. So I actually have also Wednesday, a Tuesday and Thursday lab section. So in case you guys want to make up more than one lab, you are welcome to come in on a Tuesday or Thursday section as well, in addition to the Wednesday and Friday sections you guys are having. Okay, just send me an email before you are coming. So all the lab sections this week are makeup lab from Tuesday, Wednesday, Thursday, and Friday. They all start at 2:10. Okay, so I will stop the lecture for today here, and then I will see you guys back in lecture on Wednesday. See you guys.